Welcome back to Chemistry 1510 video notes. Today we're going to do the first part of Chapter 10. And in Chapter 10, we are going to have to be able to do some Lewis structures. So the whole point of Chapter 10 is to figure out what those structures that we've been drawing look like in three-dimensional space. So there's this wordy theory. It's called the valence shell electron pair repulsion theory. It's a lot of words and makes it sound more complicated than it actually is. And so in this theory, all it's saying is that electrons don't like to be next to one another, and so they stay as far apart from each other as possible, right, because they're repelling each other. And so this repulsion gives rise to very specific shapes. So today what we're going to do is figure out how to determine what that shape is that a molecule is taking. And in order to start, we have to figure out how to count an electron domain. But first, let's talk about what an electron domain is. So an electron domain is a group of electrons. And when we count electron domains, we count electron domains as attached atoms plus lone pairs. So let's look at some examples. If we come down here and we look at CO2, CO2 has two electron domains. Now, when people look at CO2, what they should be looking at is the fact that we have two groups of electrons there, right? Or the way that we defined it up here was attached atoms. So carbon has one oxygen attached here and one oxygen attached here. The reason I like to define electron domains as attached atoms plus lone pairs is because it gets over the fact that a double bond is one electron domain, and this double bond is one electron domain. So a lot of times students will incorrectly call this 4 electron domains, and that is wrong, right? It is just 2 electron domains because there's 2 groupings of electrons around the central atom. If we look at this next example, there's 1, 2, 3, 4 groupings around that central atom, and so there are 4 electron domains. The issue with this problem is sometimes the students see the lone pairs on the chlorine and want to count them, but we are only looking at the electron domains around the central carbon atom, and so that's what we're counting. The lone pairs that are on the central atom and the attached atoms of that central atom. Now, this final example gives people a freak out because they look at it and they go, where's the central atom? Well, let's show you what I see. What I see in this structure is that half of the structure is equivalent to the other half. So many structures don't have a singular central atom, and this is one of them. If you go on to organic chemistry, you're going to be looking at big molecules that do not have a central atom, and you'll look at the electron domains as individual questions within a bigger structure. So what I mean by that is they might draw a really big structure and then point to one atom in the structure and say, what are the electron domains? And that's kind of like this one here, right? You could look at this carbon or you could look at this carbon and consider either of those your central atom. And in this case, because there's symmetry, it doesn't matter which one you choose, because no matter what, you're seeing, if we choose the pink highlighted one electron domain, 2 electron domains. So an electron domain is really a grouping of electrons where a bond is considered a grouping of electrons, a single bond is a group, a double bond is a group, a triple bond, like we're seeing here, is a group, or a lone pair is a group. The definition of electron domains that I gave you over here, or at least how to count them, is based upon the fact that a lot of times students incorrectly call a triple bond 3 individual electron domains, and that's false. Over here, we have only 2 electron domains. So the equation that I boxed in yellow is trying to kind of circumvent that misconception. So now that we've figured out how to count electron domains, let's start looking at the shapes that we're going to see. So over here, I have a table, and right now we're only going to focus in on parts of this table. So part of it, you're not going to know what it is. You're not going to know what hybridization is. You're not going to know what this SP, SP2, and so on is. And that's fine. Well, it'll become at the end of the chapter. So what I want to focus on is this regions of electron density. And the regions of electron density is the same thing as electron domains. Right, because that's what an electron domain is. It's a region of electron density. The electron density can be a lone pair, it can be a single bond, it can be a double bond, it can be a triple bond. That's a singular region. And so remember what we said was in the valence shell electron pair repulsion theory, which we call VSPER, even though it's VSPER. It's saying that pairs of electrons, like if we look at something like BeH2, that the electrons in this bond and the electrons in this bond don't want to be anywhere near one another. And so what they do is they spread as far apart from each other as possible, and as far apart as possible is along a straight line. So when you see this arrangement that we're drawing here in the table, it's like we're looking at the bonds and or the atoms, if it makes it easier for you. And at the end of each of these, where I have my little red dots, we have one of the hydrogen atoms, because those bonds that are making, or the electrons that are making up those bonds, they want to be as far apart as from each other as possible. And so what happens is we make a structure that looks like a line. In a different example, something that would be like BH3, for example. You might have wondered why, when I've been drawing Lewis structures, I always spread out my atoms, and this is why. Because the bonds that make up that molecule, the electrons in those bonds want to repel one another. And so the hydrogens of the BH3 are going to be as far apart as possible, and if we connect them, they make a little triangle, and it happens that that triangle is all in the same plane, so we call it trigonal planar. Some people might also call it triangular planar, and that's fine. So you kind of imagine, oops, sorry about that. You imagine the boron in the center of this triangle, and there's a hydrogen here, there's a hydrogen here, and there's a hydrogen here. And so those bonds are trying to be as far apart from each other as they can. The next one is much harder to draw. And so when we've drawn things like CH4 in the past, we've drawn them like so. And this actually is not an accurate representation of what CH4 looks like, because in actuality, what's happening is 2 of the bonds are in the plane of the page, and then one bond is going behind the plane of the page, and I'll draw that dashed, and one bond's coming out at you, and I'll draw that wedged. So what's happening is that when we connect these hydrogens, we're really kind of like making a tetrahedron, which is very hard for me to draw and have you know what I'm trying to draw, which is why I have this figure here, which is pre-drawn. That looks a heck of a lot nicer. Now, part of the thing that we're going to do in class is really kind of like get our hands on these models so that you can visualize them more effectively. So then if we have 5 electron domains, they set themselves up in this fashion so that where I'm drawing the dots is an atom, and in the middle is your central atom, and then these atoms are as far apart as possible. And then our octahedral structure, has 6 electron domains, and those atoms are where I'm drawing the red dots. And right here in the center where I'm drawing the blue dot is where the central atom would be. And so your central atom is connected to all of those 6 atoms. And when you try to kind of like draw a face connecting each of those atoms, you end up with 8 faces, which is where the octahedral comes from. Right? And this one up here, see how there's like a triangle in the center? Right? That's where the word triangle comes from, or trigonal. And then bipyramidal is bi is 2, and pyramidal or pyramidal is obviously a pyramid. And look, you kind of got like a pyramid shape going up here, and then you got a pyramid shape going down here. So these are our 6 main classifications of shapes. Let's break these classes down into more specific examples. So I have a series of tables here listed with electron domains and attached atoms and lone pairs. So remember that electron domains equals the number of attached atoms, which I'll abbreviate AA, and lone pairs, which is LP. So your second column and your third column will add up to your electron domain column. And so some of these shapes you've already seen on the top of the page. For example, this one right here, see how all those atoms are in a line? Right? That's linear. And so now what we need to do is start distinguishing between something called a shape and something called an electron pair geometry. In this case, your electron pair geometry and your shape are the same thing. And notice how in this picture we're showing that there's a 180-degree bond angle between the atoms that we're labeling as X. So then we move into the next shape, and the next one has, again, an electron pair geometry and the shape are the same thing. And if we kind of scooch back up really quick and look, see how this one was making something that looked like a triangle. Here is what it kind of looks like if we arrange the orbitals in this fashion. And so you can see how it kind of looks like it's making a triangle. They're all in the same plane. So we call this electron pair geometry trigonal planar. And the shape will be the same. So don't get freaked out yet. We're about to talk about the difference between shape and electron pair geometry. So the difference starts to come in when your attached atoms are no longer equal to the electron domains. And what I mean by that is, see how over here I still have 3 electron domains, but I have 1 lone pair. Now that you have a lone pair, things start to change. The electron pair geometry doesn't change. If you take off one of these atoms, the X, and you replace it with a lone pair, which is what we're trying to illustrate here, you still have electron density there. You still have 3 electron domains. So it's still a trigonal planar electron pair geometry. But the shape takes into account if we were looking at a structure and taking a picture of it, how the atoms would be arranged. So the atoms would be arranged in that highlighted way that I just drew. And the thing is, the lone pair still takes up space. But because lone pairs are made up of electrons that are very, very small, if you were to take an atomic picture of this structure, you would not see the lone pair, but you would still see its effect. You would see this kind of bent shape with respect to the X, the E, and the E. And that's actually what we call this. We call it bent. And when we start to look at the bond angles, we're telling you here that the bond angle is 120 degrees when we have a trigonal planar electron pair geometry and shape. As soon as you add that lone pair, what ends up happening is that lone pair takes up more space. And because that lone pair takes up more space, it pushes those bonds between the E and the X closer, so you end up with a bond angle that's a little bit less than 120. There are specific bond angles that you could memorize if you wanted to, but you don't have to. All you have to do is say less than 120, or if you really want to, you can call it about 117. So let's keep going. If we look at 4 electron domains, this is going to give a tetrahedral electron pair geometry. And when there's no lone pairs, the electron pair geometry and the shape will match. So notice how I have 4 electron domains in all of these examples, so all of these will be tetrahedral. But as I start to change from 4 atoms attached to now a lone pair and 2 lone pairs, what changes is the shape, which is that kind of picture of how the atoms are arranged. So here in the example of 4 electron domains, 3 attached atoms, 1 lone pair, still tetrahedral electron pair geometry, but the shape is going to be trigonal pyramid. Some people call it trigonal pyramidal, and that's fine. And then we have yet another bent. And when students are like, oh, I have 2 bents, whatever am I going to do? Do not fear. When we start to ask test questions, we ask for the electron domains and for the shape, and that will distinguish between the 2 bents. So in this tetrahedral structure, we have a 109.5 degree bond angle. In this figure, it abbreviates it as 109. It's really widely accepted as 109.5. When we add a lone pair, we end up decreasing that bond angle because that lone pair takes up more space than a bonded pair. And so that lone pair ends up pushing these bonds closer together. And when it compresses them, we ended up with a little bit less than 109.5, around 107-ish. If we add yet an additional lone pair, so this bottom example has 2 lone pairs, we'll even be less than 107, we'll be around 104-ish. So if you want to memorize those individual ones, you're welcome to, or you can just know when it's appropriate to write less than 109.5. So far, we have looked at 2, 3, and 4 electron domains. Let's move on to 5 electron domains and then 6. So here is our 5 electron domain section. In our 5 electron domain section, what we saw was that we made something that looked like a trigonal bipyramid. So we call this trigonal bipyramid or bipyramidal, whatever makes you happy. Again, when there are no lone pairs on the central atom, the geometry and the shape are the same. And so this is also going to be trigonal bipyramidal. And when you have 5 electron domains, your electron pair geometry will always be trigonal bipyramidal. Oh, pyramidally. YL. Okay. So then when we start adding lone pairs is when the shape starts to change. When I look at this second example, when I have 1 lone pair, this kind of makes, when we see it in class, it makes a seesaw, right? So imagine there's a little human right here, and there's a little human right here, and this is like the triangular part of the seesaw, and you go back and forth and back and forth and back and forth. So this one is called a seesaw. Finally, something we can actually remember. This next one, if I kind of draw it like this, doesn't it look like a T? I think so too. That's why we call it T-shaped. This one certainly looks like a line, so that one is linear. So let's notice the bond angles here. We have two sets of bond angles. This part around the center is like a trigonal planar. And so that's why you see that 120-degree bond angle. This part is like a linear, except you have a stopping point halfway through, right? You got this planar thing right in the middle. And so what you're going to find is that there's two bond angles here, 90 and 120. As you add a lone pair, it makes your 90 a little bit less. It makes your 120 a little bit less. As you add an additional lone pair, now notice how the additional lone pair took the place of one of the atoms that was around kind of like the equator, right? Like the center over here. And so what we're finding is now we don't have a 220-degree bond angle because we don't have anything in the middle anymore. And so this is going to be just about 90, a little bit less. Then once we have three lone pairs all around the middle of the equator there, then we kind of go back to a linear structure in which your bond angle is going to be 180. So let's wrap up with 6 electron domains. So here are our final sets of electron domains. We've got 6 electron domains, and when we look at 6 electron domains, our electron pair geometry is going to be octahedral. So we will see in class why it's called octahedral. It's hard to visualize on a piece of paper. And of course, when our lone pairs are 0, our electron pair geometry and our shape are the same. So both are octahedral. Because all of these are 6 electron domains, each of these are going to have an electron pair geometry of octahedral, and what's going to change is the shape. So notice here I got a lone pair, and over here I have a lone pair on the top and the bottom. So where this lone pair is on the top, what is kind of happening is this middle part's making a square. And then I have a place at the top to connect all of the pieces of my square. And so it's kind of like a pyramid with a square base. So we call it square pyramid. Some people might also call it square pyramidal. Perfectly fine. Over here, now that I have a lone pair on the top and the bottom, these all make a square. And that square is actually in the same plane. It's hard to see on the paper. We'll see that in class. And so this is going to be called square planar because all the atoms are in the same plane. With our 6 electron domains, we're back to a singular bond angle of just 90 degrees. And when we take that bottom X off, this one right here, and we replace it with a lone pair, we have about just slightly less than 90-degree bond angle. But then when we take the top X off, and now we have 2 that atoms that have been replaced with lone pairs, and they're equal and opposite one another, then we're back to straight 90, right? Not less than, because those lone pairs are opposite each other. So as you're starting to look at this, you're like, wow, this is a lot of information. Is this going to be on the test? First of all, yes, it will be on the test. And then you're going to ask, well, what are you going to give me on the test? Nothing. This entire table is going to be plastered into your brain. So, fair warning, start working on it now. That being said, I did make one change. And that change is when you have been seeing this column called molecular shape, that's something that I changed. In the real world, it is actually called molecular geometry. So when you're like, why did my teacher change the name? Because what ends up happening is when we have one that's called electron pair geometry and one that's called molecular geometry, students really struggle telling the difference between them. So I changed the word geometry to shape here so that we could discuss that what we're looking at when we talk about molecular geometry, which we're calling molecular shape, is how the atoms are arranged. Yes, the lone pairs have an effect on that arrangement, but we're really taking a picture of how the atoms are arranged. So as you go out into the world, if you see molecular geometry instead of molecular shape, just know that they're talking about what we discussed, and they're just using actually the correct terminology, and I'm using technically wrong terminology that usually gets the best results. So let's go to an example. Here we are in our example table. We're going to do a whole bunch more practice in class, but I want to give you kind of a walkthrough for one of these. So here I have some Lewis structures drawn for you. Let's first count our electron domains. Remember, electron domains were groups of electrons that are attached to the atom in question. We're worried about the central atom. So I've got one group here, one group here, one group here, one group here. That is 4 electron domains. So whenever you have 4 electron domains, you always have a tetrahedral electron pair geometry. And in this case, because you have a lone pair here, your molecular shape or molecular geometry is called trigonal pyramidal or trigonal pyramid. The bond angle for this, well, you remember that the tetrahedral's bond angle is 109.5. That lone pair makes it just a tidbit less than 109.5. If you want to do the next one as well by yourself, go ahead and pause and give yourself an opportunity to go through it. Otherwise, we can go through it together right now. Here, remember, for our electron domains, I'm looking for a bond, and a bond is a group of electrons, and a double bond is also a single electron domain. So you got 3 electron domains here. Whenever you have 3 electron domains, you have a trigonal planar structure. And because you have no lone pairs on the central atom, your electron pair geometry and your molecular shape will be the same. So this will also be trigonal planar. Finally, your bond angle is going to be 120 because remember, kind of what you're doing is you're taking essentially a circle because we're looking at something that's planar, so you can use a circle, and you're dividing your circle up into thirds, so that's 360 divided by 3, and that's where that 120 comes from. So if you need to take a little mental break, go for it, because we're going to start talking about a different concept, which is the polarity of a molecule. We have already discussed the polarity of bonds, right? If bonds are polar or nonpolar. And so now we're going to take that and we're going to expand upon it. And now we're going to look at an entire molecule and try and decide if an entire molecule is polar or not. And so in a molecule, what would happen if it was polar, what that would look like, is an unequal distribution of the electrons in the overall molecule. So there's 2 ways to make this happen. You can have, so way 1, an asymmetrical structure. Oh, sorry, that's here. Look for an asymmetrical structure. So way 1 to have an asymmetrical structure is to have lone pairs on the central atom. And way 2 is to have different atoms attached to the central atom that have varying electronegativity. So atoms with different electronegativity attached to the central atom. Let's look at an example of each of these. So here are the same structures that we saw above. And I'm going to scroll so you can still see that top part. And so what we can do is we can answer the following questions in this table. So question 1, are the individual bonds polar? Well, if we look at chlorine's electronegativity value, that's 3.0. Phosphorus has an electronegativity value of 2.1. So yeah, that bond is polar. But having polar bonds doesn't necessarily make a polar molecule. And so what we're really looking for is the molecule symmetrical? And here the answer is no. And if the molecule is asymmetrical, which it is, explain why. Well, it has a lone pair on the central atom. And it's going to be really hard to kind of see asymmetry in a molecule when you're not holding it. So what we'll do in class is we'll build some models of these and really try to recognize some asymmetry and discuss in more detail what it means to be asymmetrical. So if a molecule is asymmetrical, then it is polar. Then, in our next example, are the individual bonds polar? Ooh, it depends. All right, the CO bond is polar. The CH bond is not. The way that I know that, carbon has an electronegativity value of 2.5, hydrogen 2.1. All right, so that's only a difference of 4.4. And carbon 2.5, oxygen 3.5. So that's an electronegativity difference of 1, and so the CO bond is polar. So in this case, the molecule is asymmetrical. So is the molecule symmetrical, it's asking? And you say, no, because what's happening is we have different atoms, or atoms with differing, ing? That does not look right. Oh, you'll survive. Atoms with differing electronegativity values attached to central atom. So I always like to think of examples like this one with tug of war. So what's happening is the oxygen is pulling the electron density, its direction, very strongly. And the carbon-hydrogen bonds are like little baby arrows pulling electron density their direction. And so if you liked physics class, look at this as if it's a vector addition and say, do those vectors cancel out to 0? And the answer is a strong no, because this pink vector is huge in comparison to my little red vectors. If you don't like physics, think about it like a tug of war. It's a three-way tug of war. Carbon, the central atom, is going to be your red bandana where your 3 ropes are attached to each other. And so the big pink arrow here is showing the entire football team pulling the electrons their direction. And here is the band, and here is the orchestra. And we're assuming that they are not as strong as the football team in this particular example. And what we see is somebody very clearly wins the tug of war. And if there is a winner to the tug of war, then this means that the molecule is not sharing the electrons equally, and so this is a polar molecule. When we see each other in class, we will do more examples. So I will see you soon with more fun examples and definitely some models that we can touch and get a better visualization of. So thank you for your attention today in our first part of Chapter 10, and I'll see you soon. Katoni signing out.